Let's have a look at different types of organic isomers. This is Dr. B, and they are characterized by always having the same molecular formula, but different arrangements. We'll go over the major types here. These are each in pairs, and perhaps you can guess what the names are, but I'll go ahead and show you. Structural ones, stereo ones, cis-trans or EZ, conformational, and optical isomers. Both of these substances are C4H10, but they are clearly very different substances. This one is branched, this one is not. So structural isomers are characterized by having a different two-dimensional arrangement, a very fundamental difference. Here the difference is a little bit more sublime, right? The two-dimensional arrangement is identical, but the three-dimensional arrangement is different. Don't forget that wedges means coming out at you. Hatches means going into the board. So these two chlorines would be quite close to each other. These two would be separated. One's coming out, one's going in. If it's possible, if you own a set of molecular models, assemble some of these, and it's so diagnostic, particularly for some of the ones we're going to show later. Look at these two substances. They're both C4H8, but can you see how they're very different spatially aligned? These are really, if you think about it, structurally different, but since it involves this double bond, we say that they are just different double bond isomers. Now, if it's identical things like this cis-2-butene, you can just go ahead and use cis and trans. Cis means close, trans means far. Or if they're weird, different substituents, like that might be an ether, that might be something else, then we can use the EZ nomenclature. Z is like cis, so cis, E is the far away kind. Cyclohexane, and perhaps a couple other ring structures, do something that's fairly unique and I would say more or less obscure, but it shows its way into the lexicon of organic chemistry, so we'll have a look. Assemble cyclohexane, just C6H12, and you can arrange it perhaps the most stable way, where everything's kind of far away, or you can stick these two carbons up, shape it like a boat, and they get close to each other. Those are two different forms. Now notice that in this case the only difference is that there's a different three-dimensional arrangement, but it's by bond rotation. All of these substances have free rotation of the hydrogens here, and maybe not so much there, but for some of these, when you have free bond rotation, they're just going to take an average. They're not going to be separate substances if they're just spinning around. But these can lock in somewhat, especially if you brought them cold enough. And so you have the possibility of what they call conformational isomers. Pretty rare cases. Optical isomers are perhaps the most fascinating situations here. See these two substances, both C3H6O3? The difference is so minor, right? In fact, they look like they're mirror images of each other. If they're mirror images of each other, aren't they identical? They're not. I encourage you to make molecular models of these and try to take this one and stick it on top of that one. If you could just superimpose them on top of each other, then they're the same thing, but they're not. So they use the term non-superimposable mirror images. Take-home message, if you've got 4 substituents around a carbon, they have to be 4 different ones. And we do have 4 different ones here. And you just switch one of them stereochemically, just one for the other for this tetrahedral arrangement. You've made 2 different substances. Now consider this. The intermolecular forces are absolutely identical. The distances here are all the same. Therefore, they're going to have absolutely the same physical properties. Couple things show up, one weird, one incredibly important, right? And that is they're going to have the same physical properties. There's this obscure thing that if you put them in a plain polarized light, you'll see a difference there. That's like weird. But here's something that's not weird. Your body can only digest one of these, right? They will show up as having different physical properties. Catalysts, since they have a different three-dimensional shape, catalysts wrap themselves around these, and they can only do that if you got the stereochemistry right. So for any time you see a carbon with 4 different groups on it, that's a chiral center, and that means that it has to be spatially arranged correctly for your body to recognize it. This can be an extremely challenging thing for organic chemists to deal with, and they still make drugs to this day that actually are just what they call a racemic mixture. They couldn't get the stereochemistry right, so they just made it, if you will, 50% pure, and half the stuff your body will just ignore, or maybe even worse, let's hope not. But getting the right stereochemistry for chiral centers is a real challenge. And these two substances, their relationship has a word, they call them enantiomers. So that's a little bit about different types of organic isomers.